Hello, everyone. Let me walk you through this week's highlights on magnetism. Well, it all started back when we found these strange rocks that applied a force to some other rocks in this very strange manner. We call this magnetism. In fact, if we took two chunks of these different rocks, we noticed that when we align them in a certain way, there's an attractive force, and when we align them the opposite way, there's a repulsive force. So we called one in the North Pole and the other in the South Pole. And so, unlikes attracts. So North Pole is attracted to South Pole and vice versa, and likes repel. So North poles repel and South poles repel. We also wanted to try to isolate like a South pole by itself. When we try to break one of these rocks in half, we notice that, well, the half generates a new South and North pole. And we can keep breaking this over and over again all the way until we get all the way down to the atom level. So the property of this permanent magnet has to do with the atom as opposed to the kind of rock itself. So if we look a little bit deeper, materials that can become permanent magnets are called ferromagnetic. And there's different domains. So inside of a permanent magnet, you may have some little magnets that are in there that point in different directions. Now, when the magnetic strength is weak, all these magnetic domains are kind of point in random different directions. When it's stronger, a lot of the magnetic domains all point in the same direction, maybe with some that don't. For a very strong permanent magnet, you get all of those magnetic domains in the material to point in the same direction. We can also take some iron filings, which are ferromagnetic. So we take a little permanent magnet here and we drop some iron filings around it. We notice that these filings kind of line up with the direction that the force that they receive is. Okay. And we're going to call this the magnetic field. So these iron filings are mapping out the magnetic field around this permanent magnet, similarly to we have the electric field around charges. Earth also has a magnetic field. So the north geographic pole is actually the southern magnetic pole in the Earth, and the southern geographic pole is near the northern magnetic pole in the Earth. Now, if you look closely to these magnetic field lines, you notice how they're pretty parallel on the surface of Earth, and that's how compasses work. So here I have this compass, which is just a permanent magnet on the little needle here that allows it to move freely. And because it can move freely, the north pole is going to be attracted to the southern magnetic pole of the Earth. So here's a magnetic field line on the surface of Earth, how they're lining up here. And so again, this points to the southern magnetic pole, and this points to the northern magnetic pole, but this is the northern geometric pole, and this is the southern geometric pole. So it's kind of flip-flopped. We notice something else strange happens. Here we have this wire with no current going through it, and we have all these compasses that are going to be just pointing in the direction of Earth's magnetic field. So nothing new here, but what's strange is what happens when we apply a current through that wire. When we apply current through the wire, we notice that the compasses are now pointing in a different direction, kind of a loop around the wire. So what's happening here is we can generate a magnetic field due to currents. So it's not just a property of these rocks, these ferromagnetic materials, where the atoms in there generate a magnetic field. We can also generate magnetic fields through current. So here is a wire, and we sprinkle the iron filings around. We notice the same pattern here, where the iron filings are kind of mapping out the direction of the magnetic field. And we have a rule here called the right-hand rule, which will allow us to figure out what direction that magnetic field is. So if our thumb is the current, the fingers here are going to tell us what direction the magnetic field is going to be traveling in. We have an equation for this as well. Now, the units of magnetic field is Teslas with a capital T. And we have an equation here, B equals mu naught I over 2 pi r. Where B here, this is the magnetic field strength. This is how strong the magnet is. R, this is the distance from the wire to the point that we're interested in. I is the current through the wire, and mu is a very fancy sciencey name, the permeability of free space. It's just a constant. It's 12.566 times 10 to the negative 7th. Now, it's very close to 4 pi times 10 to the negative 7th, to like 7 significant figures. And so as opposed to using this number, we're just going to use 4 pi times 10 to the negative 7th as the value for mu naught here. All right, let's say we have this power line and that's in the air. It's carrying 250 amps of current and it's 7.3 meters above the ground. What is the magnetic field strength on the ground due to the wire? So we can use our equation here, mu naught I over 2 pi r. Mu naught is that 4 pi times 10 to the negative seventh. I, we're told, is 250 amps. And then R is 7.3 meters below the wire. We can plug all that in and we arrive at 6.8 times 10 to the negative 6 Teslas is the magnetic field strength on the ground. Now, if we loop this wire and sprinkle these iron filings, we see some other pattern kind of arise here. This pattern is very similar to the pattern that we saw when we had the permanent magnet. In fact, this is what's called an electromagnet. When we loop the wire around, we can generate a field that is identical to what a permanent magnet would give us. And we can calculate what the strength of the magnetic field is with another equation. B equals mu net I over 2R. So this is the magnetic field strength at the very center. So this equation only works at the very center of one loop of wire, okay? R is the radius of the loop. So that we have a circle. So the radius of a circle from the center to where the circle's edge is. And I is the current going through that wire. And again, mu naught is this constant that we can use in our equation. Well, if we want to make a very strong electromagnet, we want to do lots and lots of these loops of wires. So we generate something called a solenoid. That just means just a bunch of different loops of wires all together. And we can use another equation to calculate what the magnetic field is inside of this solenoid. So again, this is inside the solenoid, not around it, okay? And I like to call this the bunny equation. You see it, bunny, where B is the magnetic field inside the solenoid. Again, the permeability of free space. Now, this is the turns per unit length, so like 500 turns per meter or whatever it happens to be. And I is the current that goes through this wire here. So here we have this electromagnet which picks up scrap iron in a junkyard. This electromagnet is a solenoid with 6,500 turns per meter. What is the current needed in these coils to generate a magnetic field of 0.07 Tesla? So we can use our bunny equation here, and we can kind of, we want to solve for current. So we want to divide mu naught n to both sides to get I by itself. So we get I equals B over mu naught n. And we can plug in our values here, and we arrive at 8.6 amps is the current needed to generate that magnetic field. Here I have a radioactive rock. Now, this is emitting a bunch of charged particles that are zipping around here in this cloud chamber. If we were to apply a magnetic field to this and map out the paths that those charges are taking, we get some very strange patterns happening here. Some are very straight, some are kind of skewed and curled like this. So what's happening here is that charged particles are going to interact with the magnetic field in kind of very strange ways. So let's talk about what that looks like. So here I have a magnetic field that's pointed directly to the right. And here I have a charged particle, I call this charge A, and it's initially at rest, so it's not moving. If we were to watch a video of this progressing, you would notice that nothing happens. This charged particle just stays there. It's not affected by the magnetic field at all. If I, let's say I have another particle, charged particle B, is moving to the right, what's going to happen in this magnetic field? Well, it's just going to continue to move to the right at that constant velocity. So this is also moving as if the magnetic field isn't there at all. So it's unaffected by the magnetic field at all. Well, here's charged particle C that's traveling directly upwards. What's going to happen here is very strange. It's actually going to form a perfect circle into and out of the screen, like this. So the particle is actually undergoing this circular motion, so it's affected greatly by the magnetic field. And if I were to have it initially at some kind of angle, two things are going to happen. It's going to go in a circle and move to the right in this kind of corkscrew type pattern here that's happening, okay? So we get some very strange patterns that are happening here when particles interact with magnetic fields. Sometimes it's like the magnetic field isn't there at all, and other times it's going to cause it to move in these kind of circular patterns. We have some more right-hand rules that are going to help us determine the direction of that force. The first one here on the left, our pointer finger is the direction of the velocity of the particle. Our thumb is the force, and the middle finger is the magnetic field. Your textbook uses this one, which is also correct. Your thumb is the velocity, your finger is the magnetic field, and your palm is the force. Either one of these you can use. So here we have a positively charged particle that's moving to the left, and the magnetic field is down. So if I were to take our hand, our pointer finger is to the left because that's where the velocity of the particle is moving. Our middle finger is down because that's the direction of the magnetic field, and our thumb is pointing in the z direction. So this particle is going to experience a force in the positive z direction. Here we have a negatively charged particle. Now, negative charges experience a force in the opposite direction, so we got to be very careful here. So the velocity is down, so our pointer finger is down. The magnetic field's into the screen, so that's where our middle finger is pointing into the screen. And our thumb is to the right. So if this were a positive particle, it would experience a force in the positive x direction. Well, because it's a negative particle, it's going to experience a force in the negative x direction. Here I have a velocity down, a magnetic field up. Well, there is no part of the velocity that's perpendicular to the magnetic field, so there is no force here. So remember, a lot of times, magnetic fields aren't going to apply a force to charged particles if they're at rest, or if the particle is moving perfectly parallel to the magnetic field. There also is no force. Here I have this positively charged particle that's traveling in a region where no magnetic field is. And in region 2, we have a magnetic field that's pointing out of the screen directly at you. You can imagine this point being the tip of an arrow pointing at you, okay? And so here, as this charged particle enters the magnetic field, it's moving to the right. The magnetic field is pointing directly at you, so it's going to experience a force downwards. Well, when it experiences a force downwards, it's going to cause it to kind of curve down. And it's going to continue to do that as it moves its way all the way through the magnetic field. As it continues to move down, you see how the direction of the force is changing, constantly making it to go in this perfect half circle until it leaves the region where there's a magnetic field. Now there's no magnetic field, so it's going to continue in a straight line. And we have an equation that will tell us the magnitude of this force. So this is the force on a particle due to the magnetic field. That's what that B stands for, force due to the magnetic field. Is equal to Q, which is the charge of the particle, V, which is the velocity of the particle, B is the magnetic field, and theta, this is the smallest angle between the velocity and the magnetic field. And this gives us the magnitude of the force. We have to use our right-hand rule to determine what direction that force is going to be in. Well, if our particle is fully encased in a magnetic field, it's not just going to make a half circle, it's going to make a full circle. And we can calculate the radius of that circle using this equation, where r is the radius of the circular motion, q is the charge of the particle that's undergoing the circular motion, b is the magnetic field that it's in, v is the velocity it's moving at, and m is the mass of our particle. So for instance, let's say we have a proton that's moving in a circle of radius 0.12 meters. It's traveling at a speed of 1.2 times 10 to the fifth meters per second. How strong is the magnetic field that it's in that's going to keep it in this circular motion? So here's our equation, r equals mv over qb. I would like to solve for b. So I'm going to multiply b to both sides and divide r to both sides. So I get b equals mv over qr. Now, what I didn't tell you explicitly was the mass of a proton and the charge of a proton. But these are fundamental particles, so we have those values. So here with the mass and the charge, we can plug that into our equation that we have over here and simplify in our calculator to give us 0.01 Tesla. Here's a summary slide for this highlights. We have a bunch of different equations here along with the permeability of free space. All right, I hope this helps. Let's get to it.